Now we're going to consider a line charge. This white line here is going to represent the line charge. I've got some plus signs here. Tentatively assume that it's positively charged, although what we're going to do could accommodate negatively charged also. And we have a certain charge per unit length, uniform charge per unit length along this line charge, lambda being the charge per unit length. We want to figure out the electric field at the point xy due to the charge on this line. Now, to do that, we can think of breaking the line into a bunch of small segments, and each segment is going to create a contribution to the electric field. So we're going to take a specific segment of length delta x, and with a sample point x star within that interval, and we're going to figure out the expression for the electric field due to the charge inside of this increment based on the r vector from this sample point to the point xy. So how are we going to do that? Well, first let's get our r vector. From this point to here, the r vector is going to be, well, we're going from x star to x. So the displacement is x minus x star. That's going to be our I component. Our y component is just going to be y. Our j component is just going to be y, since from here to here the displacement is y. So there's our r vector, and I didn't put a 1, 2 or anything on it. It's just the r vector for a typical increment. The contribution to the electric field is just k q over r squared times the r vector divided by r, the unit vector. What's q? What's the charge q that gives rise to the electric field contribution due to the charge within this interval? Well, the length of the interval is delta x. Charge per unit length is lambda. So if we multiply lambda by delta x, we get the charge inside of this region. And since we've got our r vector, it's just a simple matter to write out this expression. Q is going to become lambda delta x. The r vector is going to be our x minus x star squared. Don't know why the square is there, but it shouldn't be. Just going to get rid of it. Our r vector is x minus x star I plus yj. And the r and the r squared can go together to give you x minus x star squared plus y squared to the 3/2. We're going to have the first power of, well, we're going to have the square root of x minus x star squared plus y squared here. We're going to have the square of that, which is just x minus x star squared plus y squared here. And that's going to give us this to the 3/2. So there's our expression for the contribution to the electric field. Now, without going into detail, we've analyzed the local source of the electric field for a typical increment. We're going to sum up those increments from one end of the line to the other, and that sum is then going to approach an integral as we allow the length of the interval to approach 0. So what do we get? Well, we're going to integrate this expression basically. Now we have x's and x stars. We want to leave excuse me, want to leave x and y as symbols, x, y. We don't want to integrate those out because x, y is the coordinate expression of the location of this point. The x star is what we're going to integrate. Now we're integrating that along an x-axis, so it would make sense to let x star be x when we do the integral and integrate with respect to x, but we've got x and y also that we don't want to tamper with. So we're going to let the variable of integration, which would be our x star, we're just going to let that be u. So we're integrating x minus u squared instead of x minus x star. And I've got a square on it again. Doesn't belong there. Got used to writing squares. Going to replace the x star with a u, and our dx, our delta x, will become a delta u. We're going to call that a du. And we're just using u as a dummy variable of integration so we don't mess with the x or the y, of course. So there's our integral, and it's a straightforward enough integral. Can be done by straightforward trigonometric substitution. So I'm not going to go through the details of integrating this, but you'll probably want to do that.